Good morning and welcome to, it may not be morning. Anyway, we're going to determine when the derivative might fail to exist. This is section 3.2, and we're going to do this in one day. There are 4 different cases where the derivative may not exist. Okay, so a function can be continuous, but not able to be differentiated at a point. A function cannot be differentiable and not continuous. It has to be continuous to be differentiable, but there are certain places where it's continuous and not differentiable, and that's what we're talking about today. The left-hand derivative has to equal the right-hand derivative. They have to exist and be equal. All right, so there are 4 scenarios where this happens. They're called corners, cusps, discontinuities, and vertical tangents. So let's take a look at each one of these. So our first example is called a corner, a sharp turn. One example of this is an absolute value point, absolute value function. The absolute value function is continuous all across its domain. But at x equals 0, it's not differentiable. And this might be a little bit better seen because the left-hand derivative does not equal the right-hand derivative at x equals 0. And if you draw a picture of the derivative graph, on the left-hand side, less than 0, the derivative of this function, the slope of the tangent line, is a -1. So that is graphed like this, -1. At the right hand, or on the right side of the y-axis, the slope is equal to 1. Therefore, the derivative here is 1. So you can see that at x equals 0, it's not differentiable. So at x equals 0, the function is continuous, but not differentiable. Okay, not differentiable. Let's look at an example of this, x minus 2 plus 3. X minus 2 plus 3 has a vertex about right here. Okay, we move 2 to the right and 3 up. So here we have another point of discontinuity. I'm sorry, not differentiability not existing. So that's at x equals 2. This function is continuous, but not differentiable because the left-hand derivative does not equal the right-hand derivative. The slope of the left side of x equals 2 does not equal the slope of the right side of x equals 2. Okay, let's look at cusp. A cusp is a butterfly function. Okay, so this is what a cusp looks like. It's typically a rational function. Remember when you have you have a rational exponent, you have power over root. The top number is power, the bottom number is root. The limits are headed toward vertical tangents right here, and they are undefined slopes that don't exist. Okay? And I've written that out for you, those words. So that is a cusp. A piecewise function shows points of discontinuity. This is called the step piecewise function. It's called the lowest integer function, I believe is what the name of it is. And it looks like this, every integer. And so at each one of the integer points, there is a point of discontinuity and not differentiable. Okay, so at points where this function is not continuous, that also means not differentiable. Okay? The last way that we have discontinuities, non-differentiable functions is when we have what's called a vertical tangent. X to the 1/3 is a function that looks like this. And it's different from other functions that curve like this because there's a point right here at x equals 0 where the function actually has what's called a vertical tangent. So the tangent line is straight up and down, therefore it's undefined. Okay, so the slope equals an undefined number. So then if you look at where does this function, 3x minus 6, not differentiable, you set the center equal to 0. So the center, you set the parentheses equal to 0. So 3x minus 6 equals 0. And therefore at x equals 2, you will have a point where the function may be continuous, but not differentiable. What does this one say? At what point is that one? In a rational function, which is a polynomial divided by a polynomial, any place where your denominator equals 0 is a place where you're either going to have a whole or an asymptote. Right? A removable discontinuity or a whole or an asymptote, which would be a vertical tangent. So, actually it would be a discontinuity. So, you, in order to find the places where this is not differentiable, you would have to factor and set each of the factors equal to 0. So we have x minus 5, x plus 1, and therefore our 2 points of discontinuity would be at x equals 5 and at x equals negative 1. Wherever that denominator equals 0. All right, so let's take a look at some conclusions. If a function is differentiable at c, then the left-hand derivative equals the right-hand derivative at that point. Theorem 1, if a function is differentiable at c, then it's continuous. Differentiability implies continuity. This is very important because the converse is not true. If the function is continuous, it does not have to be differentiable, and that's what we were just now showing. Let's look at local linearity. A function that's differentiable at its own tangent line close to A, when you zoom in on the point, the function looks like a line. It will look like the tangent line at that point. If you zoom in to a function at a point and you do not see a line, it does not have local linearity, and therefore it is not differentiable. So this function that we put into the calculator at x equals 0 is not differentiable, which is what we would expect for an absolute value function. It is not differentiable. It does not show local linearity at that point. Graph the function 4 minus x squared. Now here's a little trick of how we graph a derivative of the function. And first we've graphed the parabola, the quadratic function 4 minus x squared. We put that in our calculator. Right here is Math 8, where we can enter a derivative. And we can actually find the number of a derivative. The book says ender, but our calculators have been updated since this book. So you just press Math 8. You get the notation that you see here on Y2. And in order to graph something, you just put x equals x. If you want to find a specific value of a derivative, you put x equals the number, and it tells you. Also, you can do, instead of Math 8, you can do Alpha Window 3. Either way. And this tells us about what we used to have to do in the dark ages before Math 8. Example 3 on page 111 tells you about a calculator caution. You should look at that, because it says basically that if you put the derivative in of an absolute value function, it will say that the derivative is 0. The calculator will. Because of the symmetrical difference quotient formula that it uses. Please look at that on page 311 and make sure you understand that. We're not going to go through all that right now, but the symmetrical difference quotient is used on our calculators. Last but not least, the intermediate value theorem. We are not going to do an example of this, but it is just like the intermediate value theorem for a function. The intermediate value theorem said between A and B, if you have a function that is continuous, all points between FA and FB are covered or hit at least once during the reign of that function. Now, what this intermediate value theorem for derivatives says is that the same is true for derivatives, that all your derivative values are going to be hit between the derivative A and the derivative of B. So this is true when the y-axis is a function. This is true when the y-axis is your derivative or slope of the curve. Thank you very much for tuning into Calculus AB channel and viewing our videos. I'm going to be a YouTube sensation.